So today we will start discussing differential geometric aspect of.
I don't think it's explained.
Hold on a second. Differential geometric aspect. Okay, let me start again. So this is lecture 13, and today we will discuss differential geometric aspect of optimal transport. Which is one of the fundamental features of optimal transport. Okay, so we were considering this metric space aspect of optimal transport, right? So we can put the so-called Wasserstein metric on the space of measures, probability measures, and we can view, we can consider natural distance between two probability distributions. Now we can consider curves and surfaces in the space of such probability distributions, and then when you consider curves, we had, if you remember, the so-called Benamo-Brenier theorem connecting the arc length of the curve with the Wasserstein distance. Okay, but we will go a little bit deeper than that today, and I forgot to. All right. Okay. Oh, and today's lecture will be mostly a review of some of the lectures Professor Pal gave. Okay. So we consider a base manifold, our underlying space. Okay. So the base manifold in this lecture is mostly Rn with a Euclidean metric. So the usual inner product on Rn. Okay. But many of the discussion today can be extended easily. Just term by term to general Riemannian manifold. Okay. All right, and then we consider the space of probability measures now with this constraint. The second moment is finite and absolutely continuous. Okay. And this space, we learned that this space is a W2 geodesic convex. Namely, if you had any two measures, mu0 and mu1, if you connect them by a geodesic, then if mu0, mu1 is in W2 geodesic, and if the mu0, mu1 is in P2ACX, then mu t is also in P2ACX for all W2 geodesic. Okay, and such a space is the main kind of space we consider today. Okay, and then remember what the Wasserstein metric is. So we focus on this W2 distance. Okay, P equals 2. Okay, and Riemannian metric is just nothing but, of course, it's more complicated, but it's basically nothing but an infinitesimal change of distance squared. Okay, you will see some more clear aspect of it later, but this is the basic intuition. The Riemannian metric is the infinitesimal change of the distance squared, and the point is that we want to view this space with Wasserstein metric as a Riemannian manifold. So the theme is like this. Given a metric space, we learn that we can consider, even without this AC, the Wasserstein space over that underlying metric space. Okay, so from the metric space, the Px will be another metric space with the Wasserstein metric. So you can keep going, Px to Ptx and so on. Okay, And then the theme today is that given a Riemannian manifold, we want to kind of see the Riemannian structure on Px, but now more precisely P2ACX. Okay. So basic ideas. I mean, if the underlying space has some kind of nice metric structure, some kind of geometric structure, it can be extended to the space of probability measures. Okay, that's kind of the theme. Then, of course, the question is how and what should be such a structure. Okay. Okay. Now let's discuss the basic motivating ideas of how we consider such a Riemannian metric on the metric space P2ACX W2. So let's just consider a curve. Okay. So for the moment, do not worry about any kind of smoothness or regularity of such curve. So we have some curve, nice, something nice. Okay, then, so in the Wasserstein space, we have some curve, let's say. Okay. Then, at each point, it should have the derivative, which should be the time derivative of the curve. Okay. Of course, that time derivative is also a measure because you differentiate a measure, right? So then you get a measure, but the measure is a signed measure, not just non-negative measure. It's a signed measure. It can have positive and negative values, but it's basically a measure. But then we view this as a velocity vector of the curve. Then the question is, what should be a natural metric on such velocity of the curve? Okay. And the natural metric should be the following. I mean, we have, if you zoom in this picture, we have rho t and rho t plus epsilon, and you have something like this, and the derivative will be some kind of tangent vector toward this curve, to this curve. Then the size of the magnitude of this tangent vector should be approximately the same as the distance between these two kind of nearby points. Okay, in other words, this tangent vector. So the this is the velocity. So the velocity is the derivative of the distance. So this condition that the size of the velocity, the speed of this curve is nothing but the derivative of this Wasserstein distance between the nearby points. Okay, so this condition should be what we want. If we want any like a natural notion of this norm of this velocity vector, which is consistent with the Wasserstein distance, right? Am I making sense here? Of course, yes. I mean, many of these. I will shamelessly repeat many of what Professor Pai covered. Okay. No, we are not defining differential. We are defining. We want to come up with a notion of how to measure the size of velocity vector, which is consistent with the distance. Okay. No, we just have curve, and we have velocity. Yeah, there is no like direction on the road. Okay. This is just I mean, calculus thing. I mean, you can just view this as R3, and then you have curve, and then, but just this more abstract. Okay. All right. Then, how do you understand the right hand side? Okay. So, and then the right hand side. I mean, between these two, let's say, points in the space of relative measures, this W2 distance is given by, and you can compute it using optimal transport, right? So let's consider optimal transport between them. Okay, and then they are very close to each other. So in particular, when epsilon is 0, I mean, then they are the same, same measures, then their optimal transport is just identity map between the same distributions. Now we have slight change of the target distribution. So you can expect that the optimal transport should be given by, this is true, of course, by Brenner's theorem, this part. This is a convex function. But then for small epsilon, when rho t plus epsilon is uh, close to rho epsilon, we expect that the optimal transport between them will be a perturbation of the identity mapping, right? And the perturbation is again a gradient over some function, right? So this is identity mapping is a gradient of this x squared over 2. And then, so their difference should be given by gradient of some function, okay? But then it's a perturbation. So we have this like a first order term and then higher order term if you consider this expansion in epsilon. Making sense? Okay. So here, of course, this u is some function. It's not necessarily convex. Of course not. Right? Some function. All right. Okay, then the Wasserstein distance between them, I mean, scared Wasserstein distance between rho t and rho t plus 1 is nothing but this transport cost for this optimal mapping, okay? And then when we write it using this expression, then this transport, the displacement is nothing but this expression. And then if you expand this in epsilon, then you get this. So this is W2 scale, it has this epsilon scale term and then higher order term. So if you differentiate just the W2 without scale, then the first derivative will be this term. Yeah, I now understand what you mean. Yeah, I think this is okay. Yeah. Right? You don't need what? No, that is epsilon scale. Because it's scale here. So that's why it's scale here. It's little o. This means this is higher than epsilon square. So it decays faster than epsilon square. And then we take the derivative. Taking the derivative means, okay, you just take the square root, then you get epsilon term, and then the principal term is just nothing but this thingy. And then you have small order term, and then you divide it by epsilon and take the limit. Okay, so then you get this term, which is okay. Sorry, it should be square. Yeah. Right. So what you can conclude is that the scale of this quantity, I mean, which we want to be this quantity scaled, should be this. Okay, making sense? U is, of course, it depends on rho t and rho t plus epsilon, but what you know is that, of course, and that's a good question, but U is some function at the moment. Okay. But U has meaning, it is nothing but gradient U has to be the derivative of this optimal transfer mapping in epsilon.
Excuse me, Professor.
Hold on a second. Let's take Jeff's question. So what was you? U depends on T, of course, because I mean, we are doing so. We can just as fundamental just let T equals 0. Okay, then just at the I mean, U just depend on T because capital T depends on T. But what you're interested in is that even at each T, the optimal transfer between these two nearby measures is given by identity plus some perturbation. Okay. Okay. What is the question from the Zoom?
Yeah, my question is, in the general optimal transport setting, we know that this transport map is like identity minus the gradient of the Kantorovich potential. So is this U the associated Kantorovich potential for the transport?
So yeah, you can view it that way. So so this U, I mean the here, okay. So for this T epsilon is it identity minus or identity plus? It depends on your notion, right? So it's identity plus gradient of some conformity potential, right?
Right.
Plus minus depends on your convention, which one you want to take between like C convex functions and C concave functions. Okay, let's just take whatever are necessary to write down this. Okay, then this whole thing corresponds to this. Okay.
Okay. Okay.
U is kind of the first order term of this psi epsilon. Oh, sorry, it's not psi epsilon. So maybe I should this phi theta epsilon. Okay, so this is like the control potential, and then U is the first order term of the control potential. All right. Very good.
Thank you.
Okay. Other question? Okay, so this is kind of a review, but plus that our whatever is known for such velocity vector can be should be given in this way, where U is this like a first order term of the control potential. Okay. All right. And another ingredient we want to consider, this kind of another aspect we want to consider is the continuity equation. So continuity equation, no, first order in epsilon. So here, look, rho t plus epsilon is just epsilon perturbation of rho t. So you have contradiction potential as epsilon goes to 0, going to 0. Okay, so that is exactly in this expression. Yeah. Okay. Good. All right. So let's just continue this. So another aspect, important aspect, is continuity equation. It says, okay, given a curve rho t in the space of priority measures, okay. Of course, you can consider. I mean, if rho t is like differentiable, then it's like a time derivative. But then the thing is that we are not just moving. I mean, this curve is not just a trajectory of a point. It's a trajectory of particles. I mean, infinitely many particles, right? So such distribution is rho t. So it is like moving. Yeah, how can I? Each particles are moving, right? So then following certain, let's say, vector field, right? So particles are moving, having some velocities for each particle, and that velocity of each particle is like a vector field, because at each location where the particle is in, you have this vector. So you have vector field. So the thing is that the moving mass distribution corresponds to moving many particles, right? Many means really infinitely many, that correspond to vector field. Okay, that's the kind of basic idea. Okay, then how this vector field and the density change dt rho t is related. Sorry, I forgot to check it here. That is the continuity equation. And this continuity equation, another important aspect of this continuity equation is it says the mass is conserved. I mean, we are just moving particles. We are not destroying or creating any particles. Okay, so mass is conserved. Just the particles are moving. So that's the aspect of continuity equation. Okay. Okay. But at each particle level, the velocity of each particle is just uniquely determined by the particle trajectory, right? But when you see the distribution, different different particle trajectories, different set of particle trajectories will result in the same distribution, right? You came to this room following some passes, right? But there can be many passes to come to the same room with the same exact final distribution you have now. So that just suggests that this continuity equation, I mean, the corresponding to the change of the mass distribution, has many different possible vector fields VT. Okay, but at least one of them represents such a curve. But the thing is that such representation, I mean, we have many such representations for the same curve in the Wasser sense space. Making sense? Yeah, the vector field corresponding to this with this fixed is not unique. Okay. So in other words, correspondence is not unique. Okay. Yeah, so that is something we will consider. Yeah. So in the next lemma, hidden here. Okay. Right. Okay. Uniqueness we'll consider. Uniqueness modulo something we'll consider below. But before that, let me remember why I wrote this. I'm just connecting this continuity equation with a transport mapping. Suppose you have mapping, okay, between two distributions, but rho epsilon is very close to rho, so it's like a small epsilon perturbation of rho, and then your S epsilon, which is just a transport mapping, not necessarily optimal, will be a perturbation of identity mapping. Yeah, it will be a perturbation of identity mapping, right? So identity mapping plus this epsilon terms, right? Where you have the first order term b of vector field. I mean, it's from a mapping. So x gives us another like point. So this x2 vx is a vector field. Of course, here in this discussion, I'm focusing on the Euclidean case. That's why you can just exchange vector field with mappings and so vice versa. Okay. Anyways, so here, if the mapping is given in this way, then this transport condition, which gives this kind of the Jacobian determinant equation. Okay, so this means in terms of the density, it just means this, right? So this just Jacobian determinant equation just captures how this map changes the density of rho in rho epsilon. So that is exactly this equation. Okay, but now when SF is given by this perturbational identity, and if you differentiate this in epsilon, the whole equation, okay, so I forgot parentheses here, okay. If you differentiate that in the whole, in epsilon, then the result will be the continuity equation, where this vector field is so this vector field is this vector field, the same thing. Okay. So that is your exercise. Yeah, do it at home, not now. Just believe me. I may not be 100% correct, but I probably be 98% correct. So you can trust me up to 98%. Unification. Yeah, yeah, yeah. Very good, very good. So the question is, how can you summarize this kind of exercise? So the exercise just says, if you have, so exercise says that the transport mapping, if you consider the infinitesimal version of transport mapping, that is a vector field, right? Right? So, okay, so maybe. So, transport mapping, then if you consider infinitesimal version, that is a vector field. Then if you consider the condition, the transport condition, that is a continuity equation. So continuous equation is nothing but an infinitesimal version of this transport vector. Okay, that is the idea you want to remember. Okay. Okay, now regarding uniqueness of such a vector field modulo something, and okay, you can such a thing. There is this Helmholtz decomposition. I think it is first considered in electromagnetic in physics. That's why this name Helmholtz. Okay, but this has this more optimal transport friendly version. So namely, we have this like a given measure rho in this absolutely continuous in this P2AC. So this is absolutely continuous measure, and then you can consider an L2 vector field with respect to this rho. It means rho square. Sorry, B norm square D rho is finite. Okay, so given such L2 vector field, the claims of Helmholtz decomposition is that there is a unique pair W, which is a vector field, and mu is a function. Okay, so W is a vector field, change the color. U is a function, scalar function. With certain, let's say, kind of smoothness. So W is just an L2 vector field, and then U is something you can differentiate. Okay, so this is a Sobolev space, but which is a weak, some kind of weak notion of derivative. Okay, anyways, the point is that this U is something you can differentiate in some sense, okay? And W is some nice thingy. And then with a condition, if you combine this vector field with this measure rho, okay, then you can consider this this equation, divergence of this vector field equals 0, okay, in a weak sense. Okay, weak sense means, maybe for you, this means divergence rho W C dx is 0 for O to C, which is smooth and compactly supported on. Okay. And this is important thing. Your vector field V can be decomposed into this W, which is this rho divergence free, and the gradient over some function. Okay. So if you are like in the three-dimensional space, this is like your given any vector field, you can decompose it as a divergence vector field and a curl-free vector field. So that, and curl-free vector field in R3 is nothing but gradient. Okay, so this that is what Helmholtz decomposition generalized. Okay. So if you have any such vector field, basically such vector field is given by this rho divergence free vector field and gradient of u for some u. Okay. And given rho and this velocity vector rho t rho, whatever it is, something corresponding to differentiating a curve in the Wasserstein space with respect to the time. Okay, given rho and rho, partial t rho, okay, the claim is for this continuity equation corresponding to partial t rho, there's unique such vector field, okay, which is given as the minimizer of this L2 norm with respect to rho. Okay, you have many other possible vector fields, but among them, there's unique one, okay, which minimize this this L2 norm with respect to rho of such vector field. This unique minimizer, and the unique minimizer is given as A is the gradient of a function u. So you not so you can apply this Helmholtz decomposition to get this. So that is your exercise. So another meaning of this is, in other words, it means also we can say the vector field is unique modulo rho divergence free. Meaning, if you had, okay, let me just explain what I wrote here. If you had another vector field, you have, so it means if you had two vector field v1 and v2 corresponding to such such continuity equation, then v1 v2 has to be this divergence free equation. Okay, so maybe this is not that interesting, right? I mean, this is obvious, right? Because you can just plug in this V1, V2, and then this is the same. What you get this? So okay, so let me take back. So the uniqueness modulo this divergence free vector field is just something obvious, but something non-obvious is that such unique vector field is given as the gradient of some function first, and second, it is given by the minimizer of this L2 norm. Okay. Right? And maybe, yeah. So you have many vector fields satisfying this equation. Okay. And then you can consider this. So set of vector fields satisfying this equation, okay, given this partial t rho, then you can view this as a functional.
Oh, and then
Your objective function.
Right.
Then you have your minimizer is given by gradient sum. Okay. In other words, gradient u is the arg mean of this thing subject to. Okay. Right. Yeah, so this means V is a vector field. V is a mapping from RD to RD. So it's a vector field. All right, so just to give you some intuition of this Helmholtz decomposition connecting it to optimal transport. I mean, again, it's the same kind of same theme. Transport mapping and infinitesimal version is like vector field, right? If you consider this is exactly like an infinitesimal version of the transport cost. Am I making sense? W2 cost is basically what? Integral of tx minus x squared in mu zero. This is like W2 cost for the optimal transport mapping, right? So, and infinitesimal version, this is a vector field. So this integral has this infinitesimal version, just L2 integral of the vector field with respect to the given measure there. Okay. And that vector field transporting the mass is just given here, continuity equation. Okay. All right. Okay. Then why such minimizer should be given as a gradient of some function? It's just because optimal transport is given by gradient of some convex function, right? All right. Grenier theorem. Okay. So the minimizer of this infinitesimal version should be given by some kind of infinitesimal version of this gradient of psi corresponding to tx minus x. So it is basically gradient psi minus x. Okay. So it is gradient psi minus x squared over 2. So psi is convex, but psi minus x squared over 2 is not necessarily convex, but it is still a function. So this is why you can expect such a minimizer is gradient of u if you knew Grenier theorem. In fact, you can prove the Helmholtz decomposition is kind of backward way using Grenier theorem. Okay. You can prove so if you really want, you can prove this using Grenier theorem. In other words, Helmholtz decomposition, one way to view it is that it is an infinitesimal version of brand new cell. Okay? It is an infinitesimal version of brand new cell. Let me erase this. Okay. Okay, so what? So let's just try to summarize the important points. So important point is that given a curve, we can consider is kind of a velocity of the curve. So curve is like rho t, some rho t, and the velocity is like derivative of this. Okay. Okay, just let me just forget about this subscript. So rho and this partiality rho, some corresponding to the velocity of the probability measure. We had this unique gradient vector field gradient u, okay, satisfying this continuity equation corresponding to this and that. Okay, that is an important summary, important point of the previous two pages. Okay. So this just differentiating this rho t as just a density function, you get some kind of density function. But the point is, such density function can be represented by a unique by this unique vector field given as the gradient of some function, satisfying the continuity equation. Yes. Yeah, so I'm just here. I'm just assuming rho is just a rho at the initial time, and then you just move it with some rho t, and then I'm talking about this initial rho partial t is just that initial derivative at t equals 0. So okay, so we have some given rho distribution. We can consider initial like a change of the density along some curve of measure. Right? Yeah, just to write down this, yes, just so I did this at each time, right? But you can just consider the time 0, for example. Or at any point, so at each time. So at each point, you have this vector and that measure. That is like this. Okay. All right. So, okay. And we know that then the notion we want have the norm of the W2 norm of this vector, this velocity vector partial T rho, is given by the L2 norm of this gradient vector field with respect to that given rho. Okay. So this, so of course, along a curve, right? If you are here, you use this row. If you are there, then you have another row, let's say row prime, right? Then you have to use that row prime here, okay? So this kind of measuring the W2 norm of this whatever velocity depends on where you are currently, your current measure row, okay? Am I making sense? Yes. Yeah, that is somewhat okay. I'm not going to repeat his question, but which is somewhat beyond my it's a bit sophisticated. Yeah, so we are going to consider a more rigorous treatment of all this. Okay. Okay. For the moment, this is just to give you some motivation and idea. But of course, I mean, this is a key idea. Okay. And we know that this quantity is the minimizer of such L2 I mean rho L2 norm with respect to rho of all the vector fields satisfying the continuity equation. Okay. Okay, so this is how we define the normal vector field that is consistent with the Wasserstein metric. Okay, but when we consider Riemannian metric is not just about norm. So Riemannian metric says given two vectors, tangent vectors, Riemannian metric is like this. You have some Riemannian manifold, let's say M, Riemannian manifold. Then at each point, let's say X. Okay, let me use let me use X. You have two, let's say, different tangent vectors, psi 1 and psi 2. And the Riemannian metric is, it gives the derivative, sorry, the, the kind of inner product between these two tangent vectors depending on such location X, okay? So in Riemannian case, I mean, such inner product depends on the location at the Riemannian manifold, okay? The location in the Riemannian manifold. Okay, so now, so we want to view our Wasserstein space as a Riemannian manifold, and we want to define such a Riemannian metric between two, let's say, tangent vectors. Okay. So here, when I say tangent vectors, they are just nothing but the velocity vectors coming from curves. Okay. Just take it for now. Okay. Okay, then how we define it? So given two curves, we have these velocity vectors, and then each of them correspond to some gradient of some functions. Okay. And then the Riemannian metric, which is consistent with this definition, this like a W2 norm of the velocity, is nothing but this expression. You just replace this norm scale with this inner product of your underlying space. So this is the inner product at, at your location at your current location. So actually, I have to rewrite it to be more precise. So at each x, so this inner product depends on x, okay? And then you have x here, x here. If you want to consider more general Riemannian manifold, but I just wrote this just having just Euclidean space in mind. So this notation doesn't matter, but to be more precise, I should write it this way. Okay. Okay. Question. So this is the metric. The Riemannian metric on the Wasserstein space, the P2ACF. So again, two things. So these kind of so-called vector fields are represented by this gradient of some, sorry, these velocities, okay, of measures are represented by vector fields on the underlying space. And then the way we measure their Riemannian product is just do this L2 type product between this vector field with respect to the current measure.
There are two.
No, there's only one manifold here. Just we have just only one manifold, which is P2ACX, and at rho you have, okay, maybe better to write. You have two curves given by rho 1t and another curve given by rho 2t. Two manifold. Oh, okay, two manifold mean, I think you mean right. So here, yeah. So X is the underlying manifold, just RD, and then this P2ACX is kind of this infinite dimensional manifold based on this underlying. Okay. So this point rho is the, let's say you can just consider point rho as rho 1t at t equals 0 and rho 2t at t equals 0. They just have the same point at time 0, and they evolve from there. And then they have corresponding velocities usually different, okay? And then these velocities are kind of tangent vectors in this whatever space of priority measures. And then we want to give this notion of Riemannian product between these tangent vectors. Okay. Then we have this formula because we can treat these velocity vectors as from this from the previous correspondence as the gradient of this functions u1, u2, which are vector field, and then you just integrate this product, two product of this vector field with respect to rho. Okay, so this rho is the kind of the time 0 distribution of this rho 1t and rho 2t. Grad grad what? Grad t rho? What is it? The sorry, it's a sub t rho. Yeah, yeah. So this is yeah. So each curve has this corresponding partial t. I mean, these are okay. These are just two curve and then the velocity of the curve. Nothing but. Yeah. Okay. Other question? I suggest don't try to complicate things. This is nothing. Just treat this as just ID. These are just curves, and you have just point, and this curve says this velocity. That's exactly what this is. Okay. All right. But of course, we are in this more infinite-dimensional space measures. Okay. Oh, this, yeah, so you will see a lot of them. Yeah, you will see. Okay, so the question was, what's the use of this Riemannian metric or on this space? Why do you consider Riemannian geometry on the space of Plot images? Excellent question, and the pioneers like Felix Otto of all this and others made remarkable things out of this. Okay, so this is very exciting part. Okay, so you will not be disappointed. Okay.
I have a question.
Yes.
Do we get from this Riemannian metric, do we get equivalent notions of important objects in Riemannian geometry, such as like the curvature tensors and these sorts of constructions?
Yeah, that's excellent question. Curvature tensor is a bit probably out of reach. But one thing I can say, you can consider at least if I attempt today or on Wednesday, see how you differentiate a function on the spatial measures using and okay, and then get a gradient. What is the gradient? W2 gradient of the function. Then after that, you can consider the second derivative. What should the W2 Hessian of a function on the space of our measures? Okay. So that kind of thing you can consider. And another thing is that, yeah, so regarding this, like a more differential geometric notions like curvature quantities, I don't think things are well developed, but at least in the metric space sense, whether the curvature is bounded from below or from above, that kind of things are developed. Am I making sense?
Okay, thank you.
Yeah, so like, for example, I think Professor Sumik Kar already mentioned this, that the Wasserstein space P2 on RD, you can consider the metric space, and then you can still consider a notion of curvature using this like more synthetic way to define or whether the curvature is positive or negative. Then this Wasserstein space P2RD, even though RD is a flat space, no zero curvature, but P2RD has positive curvature. I mean, non-negative curvature, and sometimes some configurations has exhibit positive curvature on P2RD. I would say yes. I didn't pursue such direction myself, so I don't know the literature well about this establishing more Riemannian geometric notions in this space of quality measures. But I think, at least from my experience, I can say that it's underdeveloped.
Okay, thank you.
Underdeveloped means a lot of chances for research, but also making progress may not be easy. Okay. All right. Okay, now let's just try to be more rigorous. Okay, so in the previous discussions, I just kind of vaguely said, okay, you have curve in the space of quality measures, and the curve can be differentiated and it has some kind of velocity. partial t rho and so on, and we did all this discussion. But let's try to be more rigorous. Okay. Okay. Continuity equation. I mean, okay, maybe we have to remember what continuity equation was. Continuity equation was like this, right? The divergence rho b equals 0. That is continuity equation. Okay, continuity equation involves a differentiability of this object rho and b, but even a pointwise sense, right? At each location x and time, you need to be able to differentiate this in x and t. But kind of when it comes to distributions, you may, I mean, the measures. I think it's a good idea to generalize such a differentiability to include less differentiable measures and vector field. Okay, that's the motivation of this weak form. Okay, what is weak form of continuity equation? I mean, in any PD, weak form means you use like a smooth test functions. This, yeah, I use phi. These are just test functions, okay, meaning smooth and compactly supporting on your underlying domain. So we have this time and location. So they're smooth function and test function are smooth in their time and in the space time, and then you multiply that test function to this equation, and you integrate. Then this equation being 0 means integration of this expression times any test function is 0. Okay, it implies this, obviously. But of course, this expression requires less than this equality. For example, you have to satisfy this equation only almost every sense. You don't have to satisfy this every point. That already kind of weakens this equation. Okay, and then if you plug, and then this is like smooth, then you can kind of move these derivatives to the right hand side. Okay, then the remaining expression on the left hand side has in this case like no derivative. You can just move this derivative using integration by parts to this test function, which is smooth. That's what happened here. So here is rho, and v doesn't carry any derivative anymore, but the derivatives over here are even in there. Okay, I hope my which one? No, b sub t is just a location at time. Okay. At a given time, the vector field v is just a space-time function. So just at fixed time, it is a vector field, pt. Okay. Yeah, integration by part. I'm just checking whether my sign is correct. But hopefully I'm correct. But okay. Okay, modulo sum possible sign error. We have this on the left hand side, and the right hand side is just this expression. Just respect that this curve, whatever it is, has this initial and finite values at time 0 and time 1. Okay, that initial condition. That initial condition is respected here. Okay. All right, and Now you can easily verify this in the case when this rho t, vt are smooth. So satisfying this equation does not necessarily require differentiability in t and x. Okay? It's a weak form. Okay, and another thing is, which is what you learn, is absolutely continuous curves, AC curves, okay, in the Wasserstein space, in P2 space. So you learn this from lecture 8, right? It means this is a curve like this, so that when you measure the distance between these, that is bounded by some given function g. Okay, so this is kind of the similar to like Lipschitz condition, that the curve is kind of Lipschitz in like W2 sense. Okay, so it doesn't like oscillate too much that this rho s and this rho t with a very small short time has really large distance between them. So this avoids such cases. So the curve may not be smooth, but still kind of well behaved. Okay, then there's a relation between absolutely continuous curves and continuification, which was already covered in this lecture 8. So let me just remind you. So if the curve in the Wasserstein space in P2 is absolutely continuous, means maybe I should I want to include not just P2 but PAC. Okay. Then there is a corresponding vector field, okay, to such a curve satisfying this continuification in a weak sense, okay, and whose norm, and you can just so this vector field also is a function of time. For each time you have this vector field, and then you at each time you compute this this I2 norm. So I2 integral with respect to rho t, and then so that's at each time, and then you integrate in time. Okay. So that is kind of the yeah, there's some kind of quantity which I mean, what is this like? So at each curve, at each point in the curve, you have this like a vector field corresponding to its velocity, right? And then we learn this corresponds to the norm of the velocity. And then if you integrate that norm of the velocity along the time, so this should correspond to the arc length of the curve. So this thing corresponds to the arc length. Okay. And that arc length is finite. I mean, that, of course, for absolutely continuous curve, finite. And this is important part. Such vector field, okay. I mean, there are many representatives for such velocity through this continuification. You may have many different vector fields, but remember, there's a unique minimizer, right, given by gradient of some function. Okay. But of course, I didn't say what I mean. Enough what we mean by this gradient, right? When we have not necessarily differentiable function. This is like a W12 gradient. Anyways, so the thing is, such a thing can be approximated by gradient of smooth functions. Okay? That is what this means. So basically, this just means Vt is some kind of gradient of some function. Okay, that's basically what it means. But more precise is that it is something approximated by the gradient of smooth functions, but that approximation is good in this L2 rho t sense. Okay. And this is vice versa. If you have this object rho t and vt satisfying all these, then such rho t is absolutely continuous curve. Okay, this is what you learn. Okay, now combining this together, we now can, okay, I still have time. We now can consider what we missed to define when we discussed this Riemannian metric on the space of Cartesian measures, namely, we just talked about some vague notion of velocity vector over curve in the space of Cartesian measures, right? But now this curve should be tangent vectors to our Riemannian manifold, to our space of priority measures. Okay, so let's talk about that. So, what is the tangent space of this P2ACRD? You already learned this actually. I'm just copying from this lecture note, lecture 8. So the tangent space is nothing but this closure in L2 of this gradient of compactly supported smooth function. Okay. Okay. But just now we can we can see the points of why we want to have this. Okay, why gradient? Because each kind of velocity vector should correspond to some gradient through the continuity equation. That's what we saw before. Right? So this is what we want to have. I mean, what we have. Okay, they should correspond to some gradient. So that's why gradient. Yeah. So for any absolutely continuous curve, you have here such gradient. Okay, so that's why we have this. Okay, why L2? Because the norm, whatever Riemannian norm we want to define for such a tangent vector is this L. Oh, it's a typo. Sorry. Gradient view here. Okay. Is this L2 integral of the vector field with respect to rho? Okay. But given a tangent vector, I mean, we want to say such tangent vectors have each tangent vector have finite norm, right? You may have very large tangent vectors, but still every tangent vector has finite norm in a reasonable geometry, right? So that's why we require this finiteness. That means we consider this L2 space. Okay, why closure? I mean, at a location rho, you have different tangent vectors, right? Let's say these tangent vectors converge to something, but that object in the limit should be again a tangent vector to have some reasonable whatever geometry, right? So the limit of tangent vectors should be tangent vectors. That's why we want to have closure here. Okay, so I think I'm motivating why we have this as our tangent vector, the tangent space. Okay, then for that tangent space, we just define the Riemannian metric just in this way. This tangent space belongs to L2, so we can just make this L2 product. Yeah. great. Okay, so this is object of notation. Okay, so just yeah. So here, I think I already. Okay, so actually below line explains that, but before that, so uh, so Riemannian metric on this is given any like tangent vectors at row. The Riemannian metric is given by this, and then of course this inner product is on x depends on your location x here, okay, for general Riemannian manifold. But of course, in the Euclidean case, this is just any point. Okay, and then back to your comment. So right, this is object of notation. Given each tangent vectors, we represent it as the gradient of some functions. Okay, so this is in fact this. Okay, and then the reason why I didn't write it this way because I mean, look, this our tangent vectors are given as the limit of some gradient thingy. So that's why I just try to avoid writing directly like gradient U1. But when things are like smooth, for example, then of course this you know Riemannian metric is given by this just two integral between the gradient functions. Okay. So anyways, so when I write ux vx, this means the representing vector fields for these tangent vectors at row, which are nothing but the limit of two limit of gradient of some. Okay, so actually this is not just statistically not an usual notation because we just said this tangent space is just this space which is belongs to L2. So I'm not using actually usual notation, but in a way we already use this abuse of concept that we represented this uh, tangent vectors and space of product measures with vector field on the underlying space. So we had this abuse of concept already. Yeah. Okay. All right. Okay. I have. Okay. After this is a bit fast. So once you accept this, then okay, Benham-Brenier says this Wasser space is kind of an infimum of this energy of your curve in the space of probability measures given represented by this continuification. But this continuification and this energy can be is minimized with when this vector field is gradient ut, and so the gradient ut correspond to your velocity of the curve, and then this expression can be written as just this. You are just this. It just says this Wasserstein distance is nothing but minimum of the curves between rho 0 and rho 1, and then what we minimize is the energy of the curve, and this is nothing but the velocity squared with respect to t. So I just rewrote this Benham-Brenier using this autos metric. So maybe I should call this autos metric. Okay, another thing, then we can consider W2 gradient of a function with respect to this metric. So gradient is a metric dependent notion. If you remember, it is already here. Given any function, if you have a curve, you differentiate it, then you have this representative called the gradient, okay? Representing this derivative with respect to this Riemannian metric, and yeah, then right. So this derivative is gradient coupled so product with this the velocity of the curve. So we just have the same thing in this space of probability measures, okay, with this auto metric, and then there should be such a notion, the gradient with respect to this Wasserstein metric. Okay. So if the such gradient with respect to Wasserstein metric exists, it should satisfy this equation. That's what I'm saying. So of course, such gradient depends on the metric. If you have different metric here, then you will have different representative. So gradient is a metric dependent notion, okay? Without metric, you cannot define gradient. All right? Okay, then when we represent the curve by this continuation or the velocity by the continuation, then this whatever this product should be, this L2 product with respect to rho t with this gradient of ut. Okay, then the question is, given f here, what should be the corresponding vector field there? Okay, so at the moment, the gradient, W2 gradient f is something in the tangent space. So it should be something in the, so this is something in the tangent space. So a tan of rho, okay? But then now we want to represent it as a vector field, okay? Then what should be such an expression? Okay, then let me just do just one more thing here. For example, you can consider the Wasserstein distance, let's say sigma, and then you have rho, then you have this Wasserstein distance between them, okay? Okay. And let's consider the scale here. So let's say your function, of course, depends on rho, just given by the distance squared, Wasserstein distance squared from the fixed measure sigma. Then what should be the gradient of such a function with respect to this Wasserstein metric? So what is the gradient of, what is the W2 gradient of W2? Okay. And the answer is, such a thing is represented by, you consider the optimal transform mapping from here to there, okay? So do you consider the displacement between, by the optimal transport? So you have here, you have hx, and you have sigma tx, right? And then you consider this displacement t minus x. So this displacement is tx minus x, and the gradient vector field here is nothing but minus of tx minus x. Okay, that is what this says. Okay, and it is kind of similar to the usual Euclidean picture. If you have a fixed point here, then if you consider the distance square, then gradient of the distance square at this point has the direction, like opposite direction from sigma, right? And then the size is the same as the length of this distance in the Euclidean case. So this just result just generalize that you have the opposite direction from this tx minus x, which is this. And then, of course, this has the size. What's the size of it? Here, where W2 have rho, in this case, in this example, it's nothing but integral of x minus dx square the rho, which is nothing but W2 rho sigma square. Okay? So the size of the gradient is nothing but the W2 distance between them. So that kind of obvious feature of Euclidean distance is generalized here. All right. And of course, this is a result of the theorem you considered in lecture 9. Okay, so just review that, and then this implies this. Okay, let me start the lecture now. Okay, thank you for your attention.